Good evening, everyone. We'll discuss about the transient response of the first order and second order systems. Can you hear? The screen is visible to you, everyone. Okay. Okay. So the time domain, the second unit completely covers with the time domain analysis. Okay. So time domain analysis means we need to find the response of a system for a given input. Okay. So normally the response will be taken as C of t. Okay. And the input is taken as R of t. So for any particular system, we are representing this as a G of S, and we are expecting the output for a given input R of t, or normally you can also represent with the U of t. And the output, we represent this as a C of t. Okay, so your output equation must be represented in terms of C of t, the time domain. So for that, we need to take up different inputs. Okay, so before going to that, what do you mean by time response of a system? We'll see that. Okay. So the nature of input, the time response of a system will be depends on the nature of the input and its mathematical model of the system. Okay. So normally the input signals to any particular system cannot be known ahead of time. Okay. So that means there may be a radar tracking system or the position of a speed or a target of a particular system which need to be found. We don't know what is the particular input. Okay, so with the help of this, difficult to find the output, and therefore we need to mathematically model our system, and then we can easily estimate for a given inputs for a particular inputs. Okay, so those systems or signals are known as the standard test signals only. So we are not fully ahead of all things. Just we are taking as particular inputs which are known as a sudden shock or a sudden change in the system or a constant velocity, okay, or a constant acceleration. So these are the standard test signals. Normally these test signals will be give the behavior of any particular system for these particular signals. Okay, so the dynamic behavior of a system is judged and compared under the application of these standard test signals. So these standard test signals are called as the impulse signal, step signal, or a constant velocity signal, or a constant acceleration system. Okay, so another important signal what we use is a sinusoidal signal. Normally this is used in our electrical signals. Okay, but in our control system topic is concerned, we will discuss these four systems, four signals for the time domain analysis. For the time domain analysis, we use these four signals, and for the frequency domain analysis, we go for the sinusoidal signal. Okay, so time response of a system. So the time response of a dynamic system to input is expressed as a function of time. Okay, so that means here for a given input, so this may be impulse input here. This is a sudden shock. It is at zero time. It is going to infinity. Okay, then you can expect the output like this. And if the signal is a constant signal, then you can estimate the signal in this fashion. Okay, so it is varying sinusoidally. Okay, just you know this. I will be back in 1 minute only. Hello. So here, the time domain response consisting of the two responses. One is a transient response and another one is steady state response. So the transient response is nothing but the time taken by the system to reach its final value is known as the time transient response. Here, just you see, this is varying like this up to this point. This is a transient response because there is a sudden change in the response, and here this response is reaching the steady state position. Okay, so here this is not what the steady state response. So if you take any first order system, it is gradually increasing. The response is gradually or exponent. This is called as exponential rise. Okay, so up to this particular point, there is a change in the output. So this response is known as a transient response, and here this is called the steady state response. This is a transient response. Okay, so here the response of a system is changed from a rest position, zero position or equilibrium, and it takes some time to settle down. So that response is called as a transient response. Okay, and the response of the system after the transient response has died out, this is called as a steady state response. Okay, so yeah, at this point your response has reached the steady state value. That's why this response is known as steady state response, and this response is known as the transient response. Okay, so here the transient response depends on the system poles only and not on the type of a system input. Okay, and therefore it is sufficient to analyze the transient response using a step input only if the input is sufficient to estimate the transient response of a system. But the steady state response depends on the system dynamics, the system characteristics, and the input quantity. Okay, and it is examined and using the different test signals. So to understand the steady state response, we need different test signals. We can use the final value theorem to estimate the final steady state value of a particular system. Okay, just these are the standard test signals. You may ask to write about the standard test signals. Okay, so the first signal is an impulse signal. So the impulse signal is having the mathematical representation of delta of t. So this is representing a sudden shock. That means here in a time 0 time, it is the magnitude goes to infinity. Okay, so if you take a value of a for a time t is equal to 0, it is having set particular value of a. Okay, and for t not equal to 0, this value is going to be 0. Always delta will be, or delta of t is equal to 0 for t is not equal to 0. It is equal to some constant value a for only the value of t is equal to 0. And if a is equal to 1, that is the magnitude is equal to 1, so it is called as a unit step impulse signal. It is called as unit impulse signal. Okay, the next one is a step signal. Okay, so the step signal intimate that it is a sudden change in the characteristics of the actual input. So here up to 0 input, this value is going to be 0. Okay, then after 0, what is going on? Suddenly this value is increases to the value of a, and it is settled down at the constant value a. Therefore, this can be mathematically represented as for t greater than or equal to 0, u of t is equal to a, and this value is equal to 0 for t less than 0. That means for t less than 0, that is negative values, this value is always going to be 0. And if A is equal to 1, you can call it as a unit step signal. Okay. And then for the ramp signal, so this ramp signal indicates emitted that it is a constant velocity, it is a linear velocity. So A into t, it will give you the value of r of t is equal to at, okay, for t greater than or equal to 0, and this value is equal to 0 for t less than 0. Just you need to explain what is the ramp signal, what is the mathematical representation of that particular system signal, that's it. Okay, and if A is equal to 1, the ramp signal is called as a unit ramp signal. Okay, so for this, always the slope of this particular signal will be A, always when you change the time from 1 to infinity. Okay, for a unit ramp signal, this value is always 1. Okay, here this varies as A, 2A, 3, and so on. But for a unit ramp signal, the variation is 1, and your input variation magnitude is also 1. If this is a 2, and this is 2, like this, it will varies. So always it will have a slope of constant value of 1. Okay, so this is about the ramp signal. Then the next one is the parabolic signal. So the parabolic signal will have a constant acceleration characteristics, and it is represented by p of t, which will be equal to a t square by 2. A t square by 2, okay, for t greater than 0, and this value be equal to 0 for t less than 0. Okay, so just you have to remember these values. Okay, for step signal, it is a constant, and for a ramp signal, it is a into t, and for parabolic signal, it is a into t square by 2. Okay, if a is equal to 1, this will be called as a unit parabolic signal. Okay, and then if you take up the slope, this will be varies as a double value. It is a square value, times time is nothing but a square value. So this will be varies as a, okay, so 1.5, 2, 2, okay, so 3, 4.5, like that, it will be varies. So this is for unit parabolic signal. Okay, so these are about the standard test signals. Okay, and the relation between these signals will be represented here. So the impulse signal will be having a constant value of a, and the step signal is also having a constant value of a. But here, just you remember, t is equal to 0. When t is equal to 0 only, this value is going to be a. And here for the step signal, for t greater than or equal to 0, this magnitude is going to be a. This is the difference. Okay, and at is for ramp signal, at square by 2 is the parabolic signal. Then if you want to find out the step signal from the impulse signal, you need to make the integration. So like that, all the signals can be obtained from one signal if you integrate it. Then if you want to get the previous value, then you need to get a take up the d by dt. Okay, so that is the differentiation of parabolic signal will give you the ramp signal, and the differentiation of your ramp signal will give you the step signal. And similarly, differentiation of d by dt of step signal will give you the impulse signal. Okay, so to get the response of any particular signal, if you are having a step signal response, okay, then you can easily directly find out by integrating the step signal, then you can get the ramp signal. Then if you integrate this, again you are going to get a parabolic signal. So once you are having any particular signal, then it is very easy to find out the another signal of a particular system. Okay, so these are the important Laplace transforms. Okay, just for easy understanding, I'm giving it you. Okay, so these are very important when you are solving the problems. So the Laplace transform of your impulse signal, Laplace transform of your impulse signal can be represented as Laplace transform of delta of t, which is equal to delta of s. It is a constant, so it is equal to a. Okay, similarly, the Laplace transform of u of t is equal to u of s, and this value is going to be a by s. Just you remember these values. Okay, for impulse signal, Laplace transform of the signal is A, and Laplace transform of your step signal is given as A by S. And similarly, for the ramp signal, the input Laplace transform of input signal is going to be A by S square. And for parabolic signal, this is 2 times of A by S cube. So normally it is AT square by 2. So this will be represented as A by S cube. Normally in our problems they will mention it as A into T square. So where you need to take up only A by S cube. Okay. So these signals will be taken like this for the solving of problems. Then here we will take the first order system. So this is a standard form. Just you remember this. The standard form of a first order system is given as K by Ts plus 1. Okay, where K is called the DC gain of the system and T is the time constant of the system. Okay, so the time constant is a measure of how quickly the first order system responds to unit step input. And the DC gain of the system is the ratio between the input signal and the steady state value of a output signal. Okay, so here how to find out this? I will take a simple RL circuit. Okay, so this is excited with a DC supply. So V of S is equal to the current flowing through this one is I of S. So R plus S into L. Normal, this is a transfer function, Laplace transform of your signals, which is nothing but I of S. So the Laplace transform will be given as I of S by E of S. This is the Laplace transform of output by the Laplace transform of input, which will give you this I of S by V of S, which is equal to 1 by R plus S into L. Okay, so here I'll take the R common. So R common, then it will be 1 by R divided by this one L by R into S. So if you take a R common, this is going to be like this. Okay, so here 1 by R is gain. So K is equal to 1 by R, and the time constant T is equal to L by R. So these are the values of your electrical system. Okay, so series RL circuit. This is a series RL circuit. This is a way of finding your transfer function for a given system with the help of the mathematical equations. So these all things will be done in our first unit only to find the transfer function of a system. Okay, so if you take up RC circuit also, you are going to get the first order system. This is the standard form. If you take any mechanical system also, you are going to get the standard form of the first order system in this form. Okay, so here L by R, that is the time constant of the system, and K is the gain, which is nothing but 1 by R. So if you vary the R value, you are going gain is going to be changed, and your time constant is also changes. Okay, then you try it out for your mechanical system also. If you are having a B, okay, dashpad like this. So this is your mass, and this is fixed to your fixed point. Then this is your F, and there is a displacement X. Okay, so for this system also, if you write up Newton's law, F is equal to m into d square x by dt square plus b into dx by dt. Okay, so this can be represented as like this, m into s square into x of s plus b into s into x of s. So this is going to be s, if I take common, m into s plus b into x of s. Okay, so here this is going to be the system. Here I will represent like this: f of s is equal to s into ms plus b into x of s. So your transfer function is nothing but normal f of s by s. This is your input. If I take this one, this is your input. So this x of s by f of s. Okay, so this is going to be 1 by ms plus b. So this is also you can represent here taking the b common. So 1 by b divided by m by b into s plus 1. So here also k is equal to 1 by b, and your time constant t is equal to m divided by b. So this is a mechanical time constant. This is your DC gain. So like that, you can take up any system which is single energy storage element that can be acting as a first order system. Okay, so for this first order system, we need to find out the response by applying the inputs. Okay, so here this is the first order system given to you. This is your first order system which is given to you. So it is having a DC gain k is equal to 10 and the time constant t is equal to 3 seconds. Okay, then if you take up another system, this is represented as 3s plus 5, but this value is going to be always 1, so you need to take 5 common. Okay, so you need to take 5 common. This is going to be 1 by 5, and numerator value is going to be 5, so this is equal to k. Okay, and the time constant t is equal to 1 by 5, k is equal to 3 by 5. So this is a way of finding the DC gain and the time constant of a system. Okay, then now we will find the impulse response of a first order system. This is very, very important. Okay, so here whenever you take up input is delta of t, okay, and r of t, and what we are representing it as a step signal, and p of t, and also okay, a of t. So this is a step signal, parabolic signal, and acceleration are any system. Okay, so if delta of t, if your input is delta of t, this response is called as a impulse response. So this is your system, first order system. This is, there is no change in the system. Okay, so if you, yes, any doubt? If you take up delta of t as input, then the response is called as a impulse response. If you take up r of t as a input, then you can call it as a step response of a system, parabolic signal. So it is a parabolic response of a system like that. Okay, or you can call it as a ramp signal, ramp response, and a parabolic response. Okay, so here I will change this here. Now delta of t we are taking, r of s is equal to delta of s, so this will be equal to 1. We are taking it as a unit impulse signal. We are taking a unit impulse signal, and therefore your response value r of s is equal to delta of s. And then we need to find out c of s. So c of s is equal to k by ts plus 1 into r of s. Okay, so this r of s is equal to 1, and therefore this value I am taking it as a 1. Okay, so now we can arrange this in terms of s plus something. So c of s is equal to k. I need to write only s plus something, so t will be taken out. Okay, so this is going to be 1 by t. So we are writing here. Then after finding the c of s, then we need to take up the inverse Laplace transform. So we need to take a inverse Laplace transform for this. Then inverse Laplace transform of c by s plus a is equal to some constant c into e power minus at, e power minus at, and therefore this value is going to be k by t. Okay, and the exponential value e to the power of minus 1 by t into small t. Okay, so this one c of t will be equal to k by t into e power minus t by capital T. This is the impulse response of a first order system. Okay, then if you take up these values, then your response will be exponentially decreasing, because you take up et is equal to 0, e power 0 is okay 1, so 1 by t is 2. So like that, this will be exponentially decaying response. Now, this is a very, very important step response of a first order system. Okay. So step response means we need to give R of S is equal to A by S. Okay. So A by S is nothing but here A is equal to 1. So unit step response we are taking. So it is going to be 1 by S. So as this is a 1 by S, now your output value C of S. So this is your output response we are interested in. So C of S is equal to this value. Okay, so K by Ts plus 1 into R of S we have considered. Okay, so R of S is equal to 1 by S. So here I am substituting the input signal. Then we need to take up the partial fractions. Okay, by using the partial fractions, okay, then you can write this one as some A by S plus B by Ts plus 1. Okay, so we need to find out the values of A and B with the help of this partial fractions approach. Then you are going to get the value of K and KT for A and B. Okay, so A is equal to K and B is equal to minus K into T. So just we are substituting here for C of S. Then after writing the C of S, then we need to take a inverse Laplace transform. Okay, so this is a forced response because you are giving the input of 1 by S. So because of this, it is called as a forced response. Okay, and this one is called as a natural response. Okay, so here this response taking the inverse Laplace transform, your value is going to be K 1 by S. 1 by S is nothing but your U of T input signal 1. Okay, minus this one T by Ts plus 1. Okay, so 1 by T, we need to take a T common here. So when you take T common, this is going to be 1 by T. So T and this T will be cancelled out. So you are having value of 1 by S plus 1 by T only. So it is like S plus A. So your signal is going to be e to the power of minus A into T. And therefore you are writing this as a e power minus T by capital T. So this is your step response of a system. Okay, step response of the first order system. When u of t is equal to 1, that is a unit step response, this equation is going to be 1 minus e to the power of t by capital T. Okay, so when t is equal to capital T, when t is equal to, this is the time constant of the first order system. So e power minus 1. So this total value is going to be 0.632 times of k. 0.632 times of k, and therefore your response. So 1, when e to the power of 0, t is equal to 0, e to the power of 0 is 1. So 1 minus 1 is 0. So your response starts here. And this response is exponentially rising like this. Okay, so this blue line indicates this exponential rise in the response like this. Okay, now it is reaching the steady state value. Then if k is equal to 10 and your time constant is 1.5 seconds, okay, so this value is reaching the 63.2%. Here we have seen that the time response 63.2%, it is reached in a time constant of 1.5 seconds. Okay, so it takes one second here. If the time constant is increasing, it takes more time to reach. Okay, so here t is equal to 1 second, so it is reaching the final value here only. But the time constant is increased, it is reaching to the final value here. 5 seconds, it is going to be here. 7 seconds, somewhere else. So the time constant of the system increases, it takes more time to reach the final steady state value. Okay, so here the same system here, for one time constant it reaches the 63.2% of your final value. For a two time constant it reaches 86%. So three times it reaches 95%. Okay, normally we go for the 2% error or 5% error. So if you take up 2% error, this value is going to be 98.2. Only the 2% small error is there. So it takes 4 times of your original time constant. And if you are interested in finding the 5% error, then it takes 3 times of time constant. So you know how to find the time constant of a system. Okay, so time constant will be depends on L by R for the electrical system. Okay, or if you take RC circuit, it is going to be R into C. This is RL circuit. No, its time constant is L by R. So for RC circuit, the time constant is RC. Okay, similarly for the mechanical system, if the time constant is M by B, okay, or J by B for the mechanical rotational system, and this is for the mechanical translational system. So always the mechanical time constant is higher than the electrical time constant of a system. So this is only for the first order case. Okay, first order systems. So here with the variation of k also, the response is varying, but the time constant is one only. The time constant we are not changing, but the gain of the system is varied. So your magnitude is going on increasing. Okay, with the increase in the k, your magnitude is varying like this. It is increasing from 1 to 3, 3 to 5, and 5 to 10 like this. So this is the response of a first order system for the step input. Okay. And similarly, we need to estimate the relation between the step response and impulse response. Already we have seen that if you are having the step response, then if you differentiate this, then you are going to get the impulse response. Okay, so already in the first case we have seen with the integration from the impulse to step and the differentiation d by dt with the step response to impulse response. That's why here we are differentiating the step response into 1 minus e to the power of t by tau. Then you are going to get the uh, impulse response of a system. Okay, so d by dt of k, this is going to be 0, and you are going to get only k by t into e to the power of minus t. This is the response of your system for the impulse input. Okay, so this is the response of the system for the step response. So like that, you have to derive. So in your examinations, you may be asked to find out the step response of a first order system and explain the time constant and DC gain with the after drawing the response. Okay, so this response you have to write down. Okay, so you need to draw this response after finding the C of t value, and you can define the time constant and how many time constant it is relating to your final value. Is it clear? Any doubts on this? Anyone, if you have any doubts, you can unmute and ask me now. Yes. So here, this is a C of t. We need to find out time constant and everything. Okay. So C of t, the response is given to you. You need to find a transfer function. Okay. So this is a procedure to find out. So as we know that e to the power of ct can be represented as 3 by s plus a, and your input response is the step response, impulse response. So this is going to be 1. Okay. So this is your function c of s. Then if you separate r of s, you are going to get the transfer function of the system in a reverse way. So if the transfer function is given, you can write the response. If the response is given, you can find out the transfer function. Okay, so like that, you need to take up some problems here. I'm not going in detail about these problems. Okay, so now the ramp response. Okay, ramp response means the input will be 1 by s square. The same procedure you have to follow. Okay, so C of s we need to find out. So k by ts plus 1 into your input signal. R of s is nothing but 1 by s square. So this 1 by s square you are representing here, then this can be represented as a by s plus b by s square plus c by ts plus 1. So this is a partial fractions approach what we need to find out use. Okay, and then by using this you are going to get a response c of t. Okay, so similarly this is our original response. Okay, unit step response, and this is a ramp response. The green line is the ramp response. Okay, so as if the value of k varies and the time constant varies, then there will be a change in the error. Okay, so for a parabolic response, so we are having a 4 different inputs. Okay, one is delta of t, then the step input, then ramp input, and then parabolic input. So for all these inputs, any input may be given to you, then you have to find the response c of t. Okay, this is the question. So here we need to take up r of s is equal to 1 by s cube, then c of s is equal to k by s cube to s plus 1. Then this is again a by s plus b by s square plus c by s cube plus d divided by ts plus 1. So this is a partial fractions approach. Then we need to take up all the values of a, b, c, d. Then you need to find the response. Okay, so if you want to directly know it, then directly you can use this relation. Okay, so that is a k into t minus t. Then you integrate it. If you integrate it, you are going to get the response for the parabolic response. Okay, so just you do this one, just you find yourself. And the practical determination of transfer function. So this is a 2.2. So ఇదంతా మనకు అవసరం లేదు. Okay. First order system with a 0, so we take start of time. Now directly I will go to the second order system. Okay, ఇంకేమైనా డౌట్స్ ఉన్నాయండి ఫస్ట్ ఆర్డర్ సిస్టమ్ లో? So this is a way of finding the transfer function of electrical circuits. Already we have seen this. Okay, the mechanical system అయితే b by k. Okay, నేను m తీసుకున్నాను. You can also take spring and dashboard. Okay, so then the second order system. So for the second order system, the poles and zeros which represent the transient response of the system for the first order. Okay, but the first order system parameters are these are the t, k. Okay, and I will directly go to the transfer function here. Okay, so this is the standard form of a second order system. Okay, so మీకు ఎలా వచ్చింది కావాలంటే just to take RLC circuit. Okay, R, L and C. Okay, so this is exactly with the DC circuit, and you find out the current response by voltage response. You are going to get this. Okay, so here this one omega n is called as a natural frequency. Okay, undamped natural frequency. Okay, and which is the frequency of oscillation of the system. Okay, without damping. Then zeta is the damping ratio of the system, which is a measure of the degree of the resistance to change in the system output. So just all of you just remember this. This is a very, very important function characteristics of your second order system, which is given by omega n square by s square plus 2 omega n into s plus omega n square. Okay, so for the given transfer function, okay, so this is given as s square plus 2s plus 4. So we need to compare this with omega n square by s square plus 2 zeta omega n into s. Okay, so for this, your omega n square is equal to 4. Okay, so here the first value, omega n square is equal to 4. So omega n is equal to 2 radians per second. And then we need to compare the characteristic equation. Okay, so always just in some cases denominator numerator value may be 6. Here this may be 4 and this may be 6. Okay, so no need to go for this value, just you compare the characteristic equation. So the characteristic equation of the system is directly given as this one. This is the characteristic equation, which is s square plus 2 zeta omega n into s plus omega n. Just to compare the characteristic equation, and in this characteristic equation omega n square is equal to 4 and 2 zeta omega n is equal to 2. Okay, and therefore these values are given as 2 zeta omega n into s is equal to 2. So zeta omega n is equal to 1. Already we know that omega n is equal to 2. So zeta is equal to 0.5. Okay, so this is the way of finding the values of zeta and omega n for a given second order system. So after that, the response of a system depends on these poles. So these poles of this transfer function. So normally this is a minus b plus or minus root of b square minus 4ac by 2a. This is the formula which we use it. By using this, you are going to get the two roots. Okay, so depending on these two roots, the system will be categorized as overdamped when zeta is greater than 1. Okay, and when zeta greater than 1, the roots are going to be real only and unequal. Okay, so the roots are real and unequal. And when zeta is equal to 0 to 1, so the zeta is in between 0 to 1, the system is known as underdamped system. And you will get the complex roots. The roots are complex. And when you take up undamped system, zeta is equal to 0. So this value is going to be 0. The first value, the real part is going to be 0. And this is also 0. So you'll get plus j omega n, plus or minus j omega n. And therefore the roots are complex, imaginary, not complex. These roots are imaginary, which are located here. And another case, when zeta is equal to 1, it is known as a critically damped case. The roots are real and equal. The roots are real and equal. This is the 4 different classification of your system. Okay, so for this case, okay, so now directly I will go through the time domain response here. Okay, so for this two roots, this will be the representation. Okay, so for the two roots, normally you can represent these roots in this fashion. So this value, the real, this is the real part, zeta into omega n. So this can be represented with a zeta into omega n. Okay, and j omega d. So omega d, normally this is equal to omega n into root of 1 minus zeta square. So this length is going to be j omega d. So this value minus, I'm converting this into minus so that it will be represented as a j. Okay, so this value is going to be 1 minus zeta square. Okay, so this is a real part and this is a j omega part. Okay, omega r omega d. Okay, so minus zeta omega n plus j omega n into root of 1 minus zeta square. This term is going to be omega d. That's what we are representing here. So the resultant value, okay, you're going to get it as a omega n with an angle of theta. Okay, so where theta is equal to tan inverse of omega d divided by zeta omega n. Okay, or omega d is equal to omega n into root of 1 minus zeta square. So omega n will be cancelled out. So theta is equal to tan inverse of root of 1 minus zeta square by zeta. Like this, you will get the value of theta if you know the value of delta. Okay. So this is the response what we'll get for any second order system. Okay, for underdamped case. So underdamped means your zeta will be varying between 0 to 1 and omega n is greater than 0. This is due to the step input. Okay, so these are the time domain specifications. One is a delay time. Okay, so delay time is the time taken by the response to reach a 50% of its final value. And the rise time is defined as the time taken by the response to reach the 100% at very first time. Okay, and if you take up overdamped case, it is varies between the 10% to 90%. But if you take up underdamped system, the response is the time taken by the response to reach the 100% in very first time. Okay, and then the peak time is a time required by the system. This is very, very important. Just you go through all these definitions. Okay, so explain the time domain specifications. Okay, and you may ask to derive the formulas for this also. Okay, so just you go through all these definitions. The delay time, time taken by the response to reach the 50% of its final value, and the rise time, time taken by the response to reach the 100% at the very first time, and the peak time is the time taken by the response to reach the peak value or maximum value at very first time. Okay, and settling time, so time taken by the response to reach its final value with the 2% or 5% error, so 0.05 or 0.02. Okay, and then another one is a peak overshoot. Peak overshoot is defined as the difference between your final value to the maximum value. Okay, so here this is the delay time and time taken by the response to reach 50%. Okay, so half of the final value. And the next one is the rise time. Rise time is taken by the 10% to 90% or 5 to 95 or 0 to 10%. So normally for underdamped case, we will take it for 0% to 100%, and for overdamped systems, it will taken from 10 to 90% of the final value. Okay, and then peak time, yeah, the time taken by the response to reach the first peak. Okay, then peak overshoot, it is a response of the system at peak time to the final value. Infinity is nothing but final value. Okay, to final value. So this will be represented in terms of percentages. So this will indicate the stability of a system. And then the settling time, time required by the response to reach the reach and stay within the range about the final value of size specified by the absolute percentage value final value, that is a 2% or 5% here. Okay, so this is the time domain specifications. Okay, then the formulas, just you have to see the formulas. So how to derive those formulas? Then I will find the step response. This is another question. Okay, so this is the question number 2 in the second order system. Okay, so we need to find out the step response of the underdamped system. So here the C of S by R of S is your transfer function, and we need to find the step response. So as the step response here, R of S is equal to 1 by S. So instead of R of S, we are representing this with a 1 by S here. So after that, we need to write this one as a by S plus Bs plus C divided by this one s square plus 2 zeta omega n into s plus omega n square. So we need to find the values of a, b, c. So you will get this response. ఓకే, మీరు ఇక్కడ రెస్పాన్స్ డైరెక్ట్గా గుర్తుపెట్టుకున్నా సరే, లేదు అంటే జస్ట్ యూ నీడ్ టు క్యాలిక్యులేట్ ద వాల్యూస్ ఆఫ్ ఏబిసి. ఓకే, సో a is equal to 1, okay, and b is equal to 1, and c is equal to 2 zeta omega n. Okay, so this is going to be your c of s. Then after that, what we are doing here is, in the denominator of the second term, we are adding zeta square omega n square and subtracting zeta square omega n square. Direct ga batti kottandi idi. Okay, so just you adding zeta square plus omega n square and subtracting. So this equation will not change. Okay, so now this total value can be represented as s plus 2 zeta omega n square plus b whole square. So this response is going to be 1 by s. The numerator is same, but here this response here s plus zeta omega n square, and from this 2 we are taking omega n square common. So you are going to get omega n square into 1 minus zeta square. This is the same response. Then if you arrange this with the omega d, this is going to be omega d plus omega d is equal to omega n into root of minus zeta square. Here is there. This omega d is called as a damped frequency. Okay, then after that, just we are separating this. Okay, s plus 2 zeta, 2 times of zeta omega n is separated into zeta omega n and minus zeta omega n, because the minus. Okay, so this is also minus and this is also minus. Don't confuse that this is adding and this is subtracting. Okay, so this is a minus also, this is also minus. So here minus 2 zeta omega n. So this equation is not changed anything. Okay, then next here for the first, this one, this equation here, we are dividing this equation with the root of 1 minus zeta square and multiplying. Okay, so this value is also not changing, it doesn't change this value. So this total value can be represented here, and omega n into root of 1 minus zeta square is nothing but omega d. Okay, so here this response is taking the inverse Laplace transform. Okay, 1 by s is going to be 1. Okay, so this total value will be s. Okay, s by s square plus omega square. So it is going to be cos of omega dt. Okay, so s by s square plus omega square. So s by s square plus a square. So this is going to be cos of a into d. So a is nothing but omega d, cos omega d. But the s term is there, 1 by s plus a something or b. So this should be represented, s plus something should be represented as an exponential term, e power minus zeta omega n into t. This is a convolution function. Okay, so this will be kept as this, but omega d square by s square plus omega d square. So this is going to be sine of omega d into t. This value will be sine omega d. So 1 by s plus something exponential of e to the power of minus j omega n into t. Okay, then this can be represented like this. So here this can be represented here. So your c of t is equal to 1 minus e to the power of minus zeta omega n into t divided by root of 1 minus zeta square into sine of omega d into t plus theta. This is your response C of t. Okay, so normally this value we are taking it as a zeta 1 minus zeta square. So this is going to be 1 and this is theta. So with this sine theta is equal to 1 minus zeta square by zeta, and the cos theta is equal to, sorry, this is 1 minus zeta square by 1. So this is equal to zeta, and tan theta is equal to 1 minus zeta square by zeta. Okay, so with this here, 1 minus zeta square will be coming here, zeta is there. So this is going to be sine theta cos omega d into t plus cos theta sin omega d into t. So this is the addition of sine of a plus b, sin a cos b plus cos a sin b. So I am converting this into this. So this is your response. Okay. So when zeta is equal to 0, when this is your step response. So this C of t is nothing but your step response. So this response consisting of your sine function and also exponential function, and therefore this response will be like this. Okay, so మీకు ఇలా ఎందుకు వస్తుంది అంటే this is a sine wave. Okay, because your response is consisting of sinusoidal function, so this is sinusoidal and e power minus zeta, so exponentially decaying. So your sine function will be exponentially decaying function. Okay, so this is the response of a underdamped system. Okay, so when your zeta is equal to 0, this is called as a undamped. The response of system we call it as a undamped, but this is the response for undamped. So when zeta is equal to 0, so e power 0, this is going to be 1. Okay, then omega d is equal to omega n, then your response is going to be C of t is equal to 1 minus of cos omega n into t. That means it is always varies like this. It is continuously varying. Okay, but here this exponentially rising and okay. Okay, now so this is your response for undamped system. Okay, so here the zeta we are taking 0 less than zeta less than 1, therefore this response is like this. If you change zeta to 0.5, your response is like this. Okay, so now if zeta is equal to 0.9, so as the zeta value is increasing, there are less number of oscillations. It will comes to steady state value very quickly. If it is equal to 1, it is a critically damped system. Okay, so like this, these are the different response. This red line is for undamped system, and this blue line is for underdamped. Okay, so as your value of zeta varies, there will be variation in your responses. Okay, so here the first one, b is equal to 0 means this is zeta is equal to 0. Okay, so undamped, so it is continuously oscillating. So the system is always unstable. It will not come to steady state value. Okay, so this is also response with the different values of natural frequencies omega n. Okay, so these are the time domain specifications. Just all of you need to go through these time domain specifications derivations. It is very, very important. So with the help of this relation, C of t is equal to 1 minus zeta omega n. So this relation, with the help of this, you can find out your time domain specifications. Because for the time domain delay time, you will need to take C of s is equal to 0.5. Then you need to find out the time TD. Okay. If you take up 1, so 1 minus 1 is equal to 0, you need to get the values of TP like that. Okay. So just you go through the text for the derivation, definitely you will get any definition for this time domain specifications. So it is very, very important topic. So these are the formulas what we use for the problem. Okay. So just is given the damping ratio. Damping ratio zeta is equal to 0.6 as given, and omega n is given as 5. Okay. And therefore your system will be like this: omega n in picture. Okay. 0.6 and 5. So zeta is equal to 0.6 and omega n is equal to 5. So just you substitute here, you are going to get these values. Okay. So with the help of these values, then you can find out the rise time. So normally they will mention you some 4 by s square plus 2s plus 4. Okay. So here omega n square is equal to 4. So omega n is equal to 2. Okay. Then 2 zeta omega n is equal to 2. So 2 cancelled out. Zeta is equal to 1 by 2. So this is going to be 0.5. Okay, so for any system is given, so this is a way of finding the zeta and omega n. Once you get zeta and omega n, just you can substitute in your time domain specifications. Okay, so rise time is pi minus zeta by omega d. Okay, so pi is equal to tan inverse of this omega n will be cancelled. Okay, root of 1 minus zeta square by zeta. So all values you should take. All the values should be in radians. Your calculator should be keep in radians, not in degrees. When you are calculating these formulas, just you remember that your calculator mode will be in radians. Okay, next TP. TP is nothing but pi by omega d. Omega d is nothing but omega n into root of 1 minus zeta square. So this is 5 into root of 1 minus 0.6 square. So you are going to get this value. Okay, TS. Okay, so 4 by 0.6 into 5. So this settling time will be 1.33. Okay, so for 5% error, it is going to be 1 second. Okay, so 5% error, it is 1 second. 2% error, it is 1.33 seconds. So, okay, then peak overshoot. So peak overshoot should be obtained like this. If this is the formula, just you remember all these formulas, then you solve the problem. This is a response to your system. Okay, next, same the time response of a step response of a critically damped system. Critically damped system ki zeta is equal to 1. So your system will be like this. Okay, so C of S is equal to omega n square by మీకు ఏమొస్తుంది s square plus 2 zeta omega n into s plus omega n square. So zeta is equal to 1. So this is going to be 1. So this is nothing but s plus omega n. So you write it like this. And the step response, so this is 1 by s. Then partial fractions, just to substitute. Then this is your response. Okay. So this is your final response. C of t is equal to, this is only exponentially varied. Okay. So critically damped response, so you will respond. This is your C of t. This is with time response t. Okay. So this is 0. And this is exponentially. Okay, so this is a second order system. It's completely a second order system. Okay, for overdamped case, these are the location of the poles on the S plane, and this is your response. Okay, so here underdamped system. So overdamped means zeta is greater than 1 here, and if you solve this 0 less than zeta less than 1 here, so the roots are complex conjugate, and your response is sinusoidally varying and exponentially decaying. And in this case, zeta is equal to 0. Okay, third undamped case, zeta is equal to 0. So it is having a whole sector imaginary. Okay, and response is oscillatory. Okay, and critically damped case, zeta is equal to 1. So your response is exponentially rising. You will get a response like this, and the roots are equal and real. So they are located at the negative real axis. Okay, so the Laplace transform of different signals here. Okay, so just this is for your idea. Okay, so these are the second order system responses. Okay, just I stop here. Then we'll having some problems. Yes, we can go through these problems again. So tomorrow morning definitely I will take a class. Okay, I'll explain you the steady state error and Routh-Hurwitz criteria. Okay. So here what we have seen in our question 1. So derive the response of a unit's typical under damped second order system. Is it clear? So standard test signals, response of a first order system for unit step input. Here only I have given the unit step input. You can go through the ramp signal or parabolic signals. Okay. The next one is the sketch time domain specifications and derive the expressions for each. Just you go through this time domain specifications. Okay. Then you can go through these expressions. Okay. मेरी slides इस्तानो नेनो. Just you go through these slides. Okay. So tomorrow I will explain you how to solve these problems also. Okay.